Good morning, everyone. Today, we'll be diving into the world of matrices and the powerful technique called diagonalization. This method not only simplifies complex matrix operations, but also has profound implications in solving systems of differential equations. Let's get started. Matrices are essential in many fields, from physics to computer science. However, complex matrix operations can be challenging. Diagonalization is a technique that simplifies these operations by transforming a matrix into a diagonal form. We'll explore the key concepts behind this and see how it's used, particularly in solving differential equations. Introduction. What is diagonalization? Diagonalization is the process of transforming a square matrix, which we'll call A, into a diagonal matrix. D. This involves finding a special matrix P that allows us to express A as PDP inverse. In other words, D equals P inverse times A times P. Number 1. Powers of a matrix A to the power of K equals to PD to the power of K, P to the power of -1. Number 2. Matrix exponential E to the power of A equals to PE to the power of D, P to the power of -1. And number 3, simplifying complex systems. So why bother with diagonalization? Well, it makes several complex calculations much easier. For example, calculating powers of a matrix becomes simple. A to the power of K is just P times D to the power of K times P inverse. Similarly, it simplifies finding the matrix exponential, which is crucial for solving differential equations. Overall, it simplifies complex systems, making them easier to analyze. Why is diagonalization important? Diagonalization simplifies a complex matrix operations by transforming a matrix into a simpler diagonal form, making it easier to calculate its powers and exponential, determine its properties like rank, eigenvalues, and invertibility, and analyze the behavior of dynamic systems. Second bullet, simplifies matrix computation. Example, power of matrices. Next bullet, applications in solving systems of differential equations. Last, used in various fields like physics, engineering, and computer science. We have two key concepts. First is eigenvalues, and the second is eigenvectors. So, eigenvalue is the scalar factor by which the eigenvector is scaled by the transformation. The scalar lambda that multiplies the eigenvector v in the equation AV equals to lambda times V. Eigenvectors. An eigenvector is a non-zero vector that only changes in length, not direction, when a linear transformation is applied. A non-zero vector V for which a matrix A only scales it, meaning AV equals to lambda times V for some scalar lambda. Formula. AV equals lambda times V. AV, the result of applying the linear transformation A to the vector V. Lambda times V, the original vector V multiplied by the scalar lambda. The equation shows that for an eigenvector V, the transformation A results in a vector that is parallel to V, just scaled by a lambda.
Diagonal matrix. A diagonal matrix is a square matrix where all the entries outside the main diagonal are zero. The main diagonal consists of elements from the top left to the bottom right of the matrix. Example. A simple example of the diagonal matrix is begin 3 and 0, 0 and 5. Algorithm of diagonalization. The following procedure will diagonalize, say, 1. Find the distinct eigenvalues of A. 2. Find the linearly independent eigenvectors Vp, V2, Vn corresponding to the eigenvalues of A. 3. From the matrix P with Bi as columns, I equals 1, 2, 3, and 4. If P is orthogonal, then Pt, AP equals P minus 1. AP is the required diagonal matrix. The diagonal entries being the eigenvalues 1 and 2 and corresponding to the eigenvectors B1 and B2, Vn respectively. Invertible matrix. An invertible matrix, also known as a non-singular matrix, is a square matrix for which there exists another square matrix of the same size called its inverse, denoted as p to the power of 1, such that their product is the identity matrix I, that is pp to the power of 1 equals p to the power of 1 p equals 1. How to diagonalize an invertible matrix? Step-by-step process. 1. Find the eigenvalues. 2. Find the eigenvectors. 3. Compute the modal matrix P. 4. Compute for the P inverse. 5. Form the diagonal matrix. And 6. Final matrix A equals PDP minus 1. Real-life application. Application of diagonalization. Computing with matrices become easier if one can diagonalize the matrix. This means thinking of the matrix as a linear transformation and switching to a basis in which the linear transformation is dilation in each direction. Diagonalization is mostly used in physics, engineering, and economics to simplify the analysis of dynamic systems and uncover fundamental properties. Diagonalization includes modeling like circuit analysis, mechanical vibration, and population dynamics. Another application is in PCA, where it uses diagonalization to find the most important patterns, eigenvectors, and complex data, allowing for simpler analysis and efficient information storage in image processing, data analysis, and pattern recognition.
Significance in differential equations. Simplifying computations. Example, diagonalizing a 2x2 linear system and solving it. So, our initial value problem is x times t equals to ax times t and x times 0. So, our step 1 is find eigenvalues. So, determinant a minus lambda I is equal to 4 minus lambda times 3 minus lambda minus 2 is equal to lambda raised to 2 minus 7 lambda plus t. So, next step is find eigenvectors. A minus 5i, v equals to 0, y is equal to x. Negative 1, negative 2 is equal to 0, v is equal to 0. Number 3 steps. Form P and D. So we have here 1, 1, 1, negative 2. That is the P. A is equal to PDP raised to negative 1. So V is equal to D. Y1 is equal to C2 E raised to 2T. Number 4, change variables to decouple. X is equal to PY. X1 is equal to C1 E plus C2 PDY. So last, solve the decoupled system. Y1 is equal to 5y1. Y2 is equal to 2y2. X times T is equal to 5e5 e raised to 5t. So we have here 1, 1, 1, negative 2.